Radioactivity Lecture 2. So at the end of last lecture, we talked about the learning outcome K. Okay, the learning outcome for this chapter will not start with A because radioactivity is part 2 of nuclear physics 1. So we continue from there. In lecture 1 on radioactivity, we talked about the spontaneous and the random nature of radioactivity K. Spontaneous because there is no need for a trigger. It happened on its own. Random nature, as we observe from the data collected in example 1, there's a lot of fluctuations in the reading, so that gives the evidence for random nature. In the last lecture, we also talked about the count weight. Okay, so by measuring the count weight and the fluctuation of count weight, we actually infer the random nature. Then we talk about background radiation, okay, how it started and the significance of it. And the last part was done by the student lecturer on the effects of ionizing radiation on living things, namely on the tissues and the cells. Okay, so today we'll move on to the types of radiation. There are 3 types of radiations, namely alpha, beta, and gamma for radioactivity K. But why are there radioactivity K? So why are some of the nuclei radioactive? So we look at that now. If we look at your periodic table, okay, this is a special periodic table as you can see. Those that are radioactive, you can see the radioactive sign. So the heavy elements are the radioactive elements, namely from mass number, or rather atomic number 84 onwards. You see that they are radioactive. So nuclei with the proton number greater than 83, they are considered big. They are not stable. Why is it like that? This is because in a big nucleus, we know there are a lot of protons and neutrons. So between the protons, which are positively charged, there will be electrostatic repulsion force. And this repulsion force is larger than the strong nuclear force. So as a result, such nuclei are unstable. So how do big nucleus gain stability? Like the one with atomic number say 84. Okay, they will have to lose mass. They have to become lighter, then they can be more stable. Because when they are lighter, the electrostatic repulsion force will be smaller, assuming there's a reduction in the number of protons, and the binding force will be able to pull them together and making them more stable. If you look at the periodic table, there is this element, okay, somewhere in the middle, where the atomic number is only 43, but it's also radioactive. That is your technetium. Besides technetium, other elements, isotopes of the elements like potassium. Potassium 40 is an isotope of potassium 39. Potassium 40 is found in a banana. That's why banana is radioactive. Also found in your potato and your carrot. Okay, in addition to that, we also have carbon. Carbon 12 is stable but not carbon 14. And usually carbon 14, they are found in living things. So isotopes of these elements are not stable as well. So why are they not stable? Because if you look at this graph, on the vertical axis you have the number of neutrons, and the horizontal axis you have the number of protons. In order for a nucleus to be stable, the neutron to proton ratio must be in the golden ratio, okay, that is in this stability zone. The number of neutrons have to be 1.2 to 1.5 for every 1 proton. So if lighter nuclei are not having this neutron to proton ratio, then you find that they are unstable and therefore they will undergo decay. For nuclei that have too many neutrons, what will happen is that a neutron will be converted into a proton. If you look at the mass, no problem, is conserved. However, a neutron is neutral. A proton is positive, so it's not conserved. So there must be another particle that have a mass 0 and a charge of -1, so that the total charge, right, is 0, okay, after the reaction. So there must be an electron that is emitted at the same time. So inside the nucleus, it's possible that an electron is emitted because what happened here is that a neutron is converted to a proton. In nuclei that have too many neutrons, what will happen is the opposite. That is, the proton will be converted into a neutron. But the mass is conserved, the charge is not. So we need another particle that has 0 mass, okay, 0 mass, similar to that of an electron, but the charge here is a positive one. So what is this particle? It must be positive and have the same mass as electron. So positive electron, we call it positron. By the way, positron is not in the syllabus. So this is for your info. In your lecture notes, you can see this on page 5. Why are some nuclei radioactive? So there are 2 reasons. The first reason is because too massive. Electrostatic force is much larger than the violence in the nucleus. The second reason is because they do not have the correct neutron to proton ratio. Okay, now let's take a look at the 3 types of radiation, namely your alpha, beta, and gamma. The first one, alpha particle. Alpha particle consists of 2 protons and 2 neutrons. So this is a helium nucleus. So the symbol for alpha particle could be the alpha, or you can use He to represent helium nucleus. For beta particle, they are electrons. We only do negative charge. Okay, so the positive one is called positrons. This is just for your info. And the last one is gamma ray. Gamma ray, as the name implies, is a ray. It is not a particle. Unlike alpha and beta, they are particles. So in gamma radiation, there isn't any particles, just pockets of energy. Gamma has a very short wavelength. It is part of the EM spectrum. The wavelength is 10 to the power minus 12 meters. Now, gamma ray is also emitted when the mass is converted to energy using Einstein's mass energy equivalent equation, E equals to mc squared. So when there's a mass loss, there must be an energy created. Okay, a little bit more about alpha particle. Alpha emissions occur mostly in the heavy nuclei because the heavier nuclei need to lose some protons and neutrons. So usually they will emit alpha particles. The speed of alpha particle, the slowest among all the 3, is 0.1 c, where c is the speed of light. Because alpha particles have 2 positive charges and is quite heavy, so it moves slower. The speed is only 0.1 c, therefore it has high ionizing power. That means when it passes by the molecules, it will interact with them and ionize them. So as a result of the high ionizing power, it tends to lose energy faster and therefore it cannot travel far. So it has low penetrating power. It can be stopped by 0.1 mm thick of paper and the range in air. So if you have an alpha particle source, all you need to do is use a pond to handle it because the range in air is only 2 cm. So if it's 2 cm away from you, technically the radiation can't cause much injury. Deflection by E field. Because your alpha particle is a positive charge particle, so if you have an alpha emitter here, okay, so once the alpha is emitted, there is a E field, region of E field. So being positive, it will be attracted to the negative side. So there will be an electric force to the left. And the path here is the parabolic path. That is to say, all the equations in kinematics, right, can be applied here. Deflection by magnetic field, yes, because alpha particles, when they are moving in a magnetic field using Fleming left-hand rule, there will be a force. So the force on the alpha particle, right, is such that it is always directed towards a fixed point. So it is a circular path. Observation shows that all alpha particles, right, will follow the same track. So the first alpha particle emitted, this is the path. Second, third, fourth, and so far so on will follow the same track. So what can you deduce about the kinetic energies of the emitted alpha particle? And what can you say about the velocity of this alpha particle? Well, we can say they're the same. Why? Because in this case, the magnetic force provides the centripetal force. If you recall the equation for magnetic force, which is BQB, V is the velocity of the alpha particle, Q is the charge, B is the B field. This must provide the centripetal force, which is equal to mv squared over r. M is the mass of alpha particle, r is the radius of the path. So if you were to cancel the v on both sides, you end up with b qr equals to mv. So mass is constant, r is constant, q is constant, b is constant. That means the velocity of the alpha particle must be the same. Okay, let's take a look at example 2. Here we have a stationary nucleus. It undergoes spontaneous decay. Alpha particle is emitted. The kinetic energy of alpha particle is given as E alpha. You're asked to calculate the kinetic energy of the recoiling nucleus. Okay, let the recoiling nucleus be X. Okay, and you're asked to express the kinetic energy in terms of E alpha. So let the recoiling nucleus be X. There's a typo error in your lecture notes. The mass number for X should be 216. Why 216? Because if you balance the mass, right, on the left hand side you have 220, on the right hand side you must also end up with 220. So alpha is 4, X must be 216. Okay, the approach to this question is, because the decay is spontaneous, there is no need for external trigger. There's no external force involved. So we make use of the concept conservation of momentum. Okay. The Ke of X, right, will be half mv squared. So making use of the concept of conservation of momentum, because there's no external force, the total initial momentum must be equal to total final momentum. Initially, there's only one nucleus and it's stationary, so the initial momentum must be 0. Okay, final momentum must be that of alpha plus X, and these two must add up to give me 0, so they must be opposite in direction and equal in magnitude. So from that, I can actually get the ratio of the velocity. So velocity of X is the ratio of the mass times the velocity of alpha. Okay, the denominator here is mx, the mass of X. Solving the equations, or rather from here, right, Ke of the recoiling nucleus is half mx Vx squared. Replace the Vx and express it in terms of V alpha, then you will be able to get a coefficient with E alpha, and that coefficient is 1 over 54. So that means the kinetic energy of your recoiling nucleus is 1 over 54 that of alpha particle. So in an alpha decay, right, the kinetic energy of X as well as the alpha particle, they are in a fixed ratio. They are in the fixed ratio, that's why the velocity of the alpha particle emitted are all following this. The velocity of all the alpha particle emitted are all the same, and therefore they all follow the same track. Beta particle usually occur in the lighter nuclei that have the wrong neutron-proton ratio. Because it's lighter, so the speed is faster. The speed of an alpha particle is approximately 0.9 c. And because it travels faster, it only have a single charge, therefore it is less ionizing than alpha particles. So it interacts less with the surrounding particles and causes less ionization. As a result, it does not lose much energy and therefore it has a higher penetrating power than alpha particles. It can pass through paper, but it can be stopped by 5 mm thick of aluminum. The range in air is about 5 meters. Deflection by E field, yes, because beta particles are negative, right? So they're electrons, they will be deflected to the positive plate. But if we were to repeat the experiment and observe the deflection, this is the first alpha particle, then you have the second and third alpha particle. Notice that they are not following the same path. Okay, there is a deviation. So there's a dispersion of particles. What about deflection by magnetic field? Because they are negatively charged. So using Fleming-Leffler rule, you find that they are also deflected. And again, observation shows that there's a dispersion of particles. That means they all do not have the same path, the same radius. So what can you deduce about their kinetic energies? Their kinetic energies are different because if I use the same concept, magnetic force provides the centripetal force. I will have BQV, where B is a B field, Q is the charge of the electron. In this case, I replace with E, and V is the velocity of the beta particle. This will be equals to centripetal force, which is mv squared over r. So from here, I can see that BER equals to mv. Because the r is not the same, and B, E, M, they are constant, that means the R must be proportional to your velocity V. So the larger the R, the larger the velocity. The smaller the R, the smaller the velocity. So having different tracks here, that means they are all having different radius. And therefore, beta particles are emitted with different velocities. So why alpha particles are emitted with different velocities? We saw in example 2, right? For the case of alpha and X, the Ke, that is the kinetic energy of the alpha particle, and the recoiling nucleus, they are in a certain fixed ratio. So the velocity should be fixed. But experiment on beta particles shows that they are not fixed. So it took scientists many years to find out the answer why that the speed of the beta particles are not fixed, even though they are emitted from the same source. The reason is because there is a presence of a third particle, which is called the neutrino. Okay, the neutrino will share some of the energy with the recoiling nucleus as well as your beta particle. So it's a three particles emission after the decay, not just your beta and the recoiling nucleus, but plus neutrino. It took scientists many years to discover neutrino because it has no charge. Therefore, it will not get deflected in both B field and E field. It has no mass. Okay, so any experiment that involve weight mg will not be able to detect them. So it is also called a ghost particle. The scientist who came up with the idea of neutrino, he actually said that he had done a very terrible thing because he has postulated a particle that cannot be detected. Okay, so it took them many years before they finally managed to prove that neutrino exists in the experiment of beta. Finally, it took them many years to identify neutrino, which is emitted in the beta decay. Okay, next one, gamma ray. For gamma, it is emitted when an excited nucleus returns to its ground state. So in alpha and beta decay, what will happen is that the recoiling nucleus, there is a daughter nucleus, usually will be in an excited state after the decay. So they will have to return to ground state. So when they return to ground state, energy has to be given out. So it's given out in a packet, which we call photon. So a gamma photon is given out. Gamma is not a particle, it is an EM radiation. So if you look at the EM spectrum, okay, on the low wavelength side, you can see the wavelength is large, not low wavelength, sorry, low energy side, long wavelength. You can see that wavelength is large, so the energy is small. Because from quantum 1, we know that the energy, right, of a photon is hc over lambda. So the energy is inversely proportional to the wavelength. The radio wave having the largest wavelength will have the least amount of energy. Then if you slowly go down, okay, your gamma ray actually is at the highest end of the EM spectrum. It has the largest amount of energy. The wavelength is also the shortest, of the order of 10 to the power minus 12 meters. Shorter than that of X-ray, which is of the order of 10 to the power of minus 10, with 10 nano, so it's 10 to the power minus 10 meters. Sorry, 0.1 nano. X-ray should be 0.1 nano. 10 nano is somewhere between UV and X-ray. Gamma particle have no charge because it's not a particle in the first place, right? So gamma ray, no charge, not deflected by B field and E field. And during gamma decay, there's no change in the composition of the nucleus. So usually nuclei will undergo gamma decay if they are in excited state. Okay, now if you look at page 6 of the lecture notes, what we have discussed, you can find them there. It's summarized in a table for you. I need you to fill in the blank. If you look at the row that says deflected in electric and magnetic field, okay, there is A, B, C. I need you to identify A, B, C. Which one is alpha, which one is beta, and which one is gamma. Okay, if you look at the direction of the E field, it is from right to left. Okay, we know that E field point from high potential to low potential, so that means the positive plates, right, should be on the right hand side, and the negative plate is on the left hand side. So you got A, right, is attracted to the negative plate. This must be your alpha. B, neutral. This must be your gamma. C, attracted to the positive plate. So this must be your electron, beta particle. Anyway, from the dispersion, right, you can see the spread, the dispersion of the path. You know that this must be beta. Okay. That is the electric force that exerts on the alpha particle as well as your beta particle. Same thing over on this side, we have A, B, and C. So you can actually use your Fleming left hand rule to find the direction of the magnetic force. Or same reasoning, you can just look at the track. C, there's a dispersion, so this must be beta. Okay, B, no deflection, must be your gamma. A, deflection, the other direction, so this must be your alpha. Okay, so that is the answer for the blanks in page 6. So let's take a look at checkpoint 1, which is below page 6. Why is gamma radiation preferred over alpha or beta for use in medical field? Okay, in the context of, say, treating the tumor. Okay, over here, this patient, we would like to treat him for tumor, which is found on this side of his head. Okay, in cases like this, we would like to reduce the pain that the patient is suffering. So if the treatment can be done outside the body, it will definitely be the option. So in this case, because the gamma radiation has the highest penetrating power, and therefore we actually do not perform surgery. We do not need to cut the patient in order to treat the tumor. So external gamma source can be used from outside the body. so that the patient need not worry about the physical wound after the treatment. So over here you can see in this diagram, this is illustrating the penetrating power for alpha particle. As we discussed, it is stopped by paper. Beta particles can pass through paper, but it will be stopped by the human body. As for gamma, it can pass through paper, penetrate through the body, can be stopped by lead. Okay, now we look at example 3. Which line in the table describes the nature of alpha radiation, beta radiation, and gamma radiation? Okay, so just now we mentioned alpha particle are helium nuclei. You have 2 protons and 2 neutrons, so answer is B or D. Beta radiation, we only do electrons, so again answer is B or D. Gamma radiation, in B it says uncharged particles. This is wrong because gamma radiation is not a particle. It is a photon. It is an EM wave. So it must be packets of wave energy. Okay, packets of wave energy is actually your photon, which is a packet of wave energy. Let's take a look at example 4. Here we have a radiation from a radioactive source enters an evacuated region in which there is a uniform magnetic field perpendicular to the plane of the diagram. So it's not mentioned whether the field is into or out of the plane. This region is divided into 2 by a sheet of aluminium about 1 mm thick. So this is aluminium here. The curved horizontal path followed by the radiation is shown in the diagram below. So there is a curved path. So which of the following correctly describes the type of radiation and its point of entry? So firstly, we can see that the radiation can penetrate through the 1 mm thick of aluminium. Okay, so it passes through, that means it can't be alpha. And because there is a curved path in the B field, it cannot be gamma because gamma will not be deflected at all. Okay, so answer is C or D. Then how do we see where is the point of entry? Well, when the beta particle pass through the aluminium, right, some of the energy is lost. So the K after passing through the aluminium will be lesser than the Ke before passing through the aluminium. So from magnetic force providing the centripetal force, we know that velocity V, right, is proportional to the radius R. You can see in this region, nearer to the X, the radius of the circle is smaller. And in the region nearer to the Y, the radius is bigger. So if V is proportional to R, larger radius means larger velocity. So the point of entry must be from Y. Because after passing through the aluminium, the speed decreases and therefore the radius gets smaller. So answer is D. Let's move on to the next page, which is about half-life and activity. Half-life, for those who take chemistry, is the same as what you have defined in your chem. The half-life is defined as the time taken for half the number of nuclei of a radioactive element to decay. Okay, because radioactivity is spontaneous, not dependent on external factors such as temperature or the chemical composite. So as a result, you find that the half-life of the radioactive element, of almost all the radioactive elements are more or less constant. The next term that I would like to define is the activity. The activity of a radioactive material is the number of decays or the number of disintegrations per unit time. So if let's say a radioactive material give out 5 radiations in 1 second, then we say the activity is 5. The unit for activity is becquerel after the French scientist Henri Becquerel. So 1 radiation per second is called 1 becquerel. If there are 5 disintegration per second, then it's 5 becquerel, and so on. If I say n naught is the initial number of atoms and n is the number of atoms left at time t, then to find the number of atoms that have disintegrated, I will have to take the initial number minus the number at time t. Say for example, n naught is 10, so I started with 10 atoms, and after some time later, after t time, the number of atoms left become 5. So how many atoms have decayed? I will take 10 minus 5, which I end up with 5. So the number of disintegration will be 5. However, when we find change, right, we always take final minus initial. So if I take n minus n naught, I'll end up with 5 minus 10, which is minus 5. So to get rid of the negative sign, I add a negative in front of minus dn. So minus dn will be the final number n minus n naught. And with that, we can form an equation for activity. This is the defining equation for activity, which is minus dn. Minus dn is the number of disintegration divided by dt, so it's per unit time. So activity is the number of disintegrations per unit time. So this gives you the defining equation for activity. Okay, so we skip this one. Okay, we skip this one. Okay, we come to checkpoint 2. In checkpoint 2, right, on page 8, you're given a table. What you need to fill in is that you're given the initial amount of iodine is x naught. So there are x naught number of iodine. What would be the amount of iodine remained after n half-lives? So initially times 0, right, number that decay will be 0. Amount left will be the total amount, which is x naught. After one half-life, half of x naught will have decay. The amount left will be 1 minus half x naught. So it's half x naught. What about after two half-life? The amount that have decayed will be half of whatever that is remain. So it's half of half x naught. But not forgetting that initially there are already half x naught of the element of the atoms decayed. So I must take the initial total that have decayed in the first half-life plus the number of decay in the second half-life. So the total number that have decayed in two half-life will be 3/4 x naught. Okay, then the amount remain to be x naught minus 3/4 x naught, which is 1/4 x naught. So do the same thing for three half-life. In the third half-life, another half of whatever remain, another half of 1/4 x naught is going to decay. Then I must remember to plus back the 3/4 x naught. So I will end up with 7/8 x naught. Then the amount that have decayed will be 1/8 x naught. What about n half-life? Okay, let's take a look at this column. This one is easier. The amount that have remained. One half-life is half x naught. Two half-life is 1/4 x naught. 1/4 is half the power of 2. When it's three half-life, is 1/8, which is half the power of 3. So when it's n half-life, looking at the pattern, it should be half the power of n x naught atoms or elements or amount that remain. What about the number that have decayed? Well, if you have this left, so the amount that have decayed must be the original number, which is your x naught, minus half the power of n x naught. Okay, so if you factorize out x naught, so it's 1 minus half the power of n x naught. Okay, so in general, right, the amount of radioactive material that remain is given by x, and x equals to half the power of n x naught, where n is the number of half-life and x naught is the initial amount of the radioactive material. So x can be, say, the number of atoms, the number of nuclei, n, or it could be the activity. It can also be the count rate or the mass of the material. So whatever that you measure, anything to do with radioactivity, it will obey this equation. Okay, let's take a look at example 5. In example 5, you're given a half-life of the radioactive element is 7/8 of a given quantity, decay in 12 days. So what fraction remains undecayed after 24 days? So if 7/8 of the quantity decays in 12 days, what is left will be 1/8. So 1/8 is half the power of 3. That means 3 half-life has passed. So 3 half-lives in 12 days. That means 1 half-life is 4 days. 24 days, after 24 days, the number of half-life will be exactly 6 half-life. So the fraction that remains will be half to the power of n, where n is the number of half-life. So it's 6 half-life. So answer is B, 1/64. Okay, so we stop here. We will continue in the next lecture.